In the second part of this unit, we'll look at compressing repetitive texts. So instead of just looking at individual characters and how to best represent each individual character, we will now try to exploit longer repetitions. So one example of this is this. If you're a fan of old Stanley Kubrick movies, you will recognize this. Maybe it's not the most natural text, but it's definitely one that shows a lot of repetitive redundancy. Although, if you work out the character frequencies, it's probably not very compressible with Huffman codes. Because, well, it's standard English text. It will be compressible a little bit, maybe to 80%, but not much more. Now, what is a natural text is hard to define. That depends on applications. But it just tends from experience to often have this type of repetition where the same word occurs many times, but not so much to an extreme extent the character frequencies. So as I said, Huffman won't compress this very much, but of course it is compressible by recognizing that it's the same phrase over and over. Now, what we would like to do is to formalize this to not encode individual characters, but whole phrases of the source text with a single code word. That sounds much more promising because it could mean that a long part of the input is represented with just a very short code word. But of course there's many possible long parts in the text, so how should we go about this? How should this work? That will be the topic of this part of the unit. We'll start with a simple example of compression that exploits repetitive redundancies, and that's run length encoding. That's maybe the simplest form of a repetition that it exploits, namely runs of a single character. Like in this image, say it's a black-white scan of some text. So every individual pixel, I hope you can see the individual numbers. This is all zeros, and then their ones start to appear. You have many runs, especially of the zeros. There's entire lines that consist of only zero repeated all over. So if we consider just the binary input, the binary alphabet, there's runs all over the place, and it seems like we should be able to compress this with a simple trick. Now, the trick here will be to use runs as phrases. So you decompose your bit string, the source text, into, well, all zeros, then a number of ones, then the number of zeros, then a number of ones, and so on. So what's convenient about the binary alphabet here is, if I currently had zeros, and I continue with the current phrase as long as I have zeros, the only thing that can happen next is to have a 1. There's just no other option. That makes this case a little more convenient, a little more efficient. That's why we discussed this. But you can extend the idea for larger alphabets in a similar way. How should we compress those? A simple way to do it for binary source text is as follows. We store the first bit of S, that could be either 0 or 1, and then for each of the consecutive phrases we store only the length. Because for the first phrase we know explicitly, we have explicitly stored which bit it's repeating, and for every other we know it's just the opposite of the previous one. So if you take our example, this string is the example I mean here. We start with a 0, that's why we say 0. The first run has 5 zeros, so that's the 5. Then we have 3 ones, that's 3, and 4 zeros, that's 4. That's it. That's run length encoding. Very simple, very neat. Now there's one issue. These are decimal numbers. I just wrote them down here for humans. But this is not a coding scheme in the sense how we defined it. because it's not so clear how to encode those numbers in binary. In particular, note that there's a priori no bound on how long a run is. We actually are very lucky or very happy if we find a very, very long run in the input. So we should expect this k, the length of the run, to be an arbitrary integer. It could be arbitrarily large. How should we represent this? How should we encode this with just zeros and ones? At that point, I would like to pause for a second and ask this question to you. How would you do this? Suppose you want to encode a string in binary and you don't know how long it is. What would you do? So it's just as an open question. So I'll give you a little more time. Just write a brief, well, try to be very brief in how you describe it. I think there's one core idea that makes this possible. If you have this idea, it should be possible to very concisely describe this. So let's give this a try. As you might see, I tried to include many more interactive questions to get some more feedback from how much you're following, how well you're following, and also because it's easy to fall into the TV doze mode if you're watching videos. I know this very well. Again, if you feel I'm wasting your time and you're already all done, if you want to let me know through the chat, we can also move on. Okay, the first people are through. And some more. All right, so it seems 2 minutes is the sweet spot, maybe 2.5. Okay, let me stop it now, just so that we see what you voted. Oops, didn't work. All right, that's hard to read. Maybe do the table instead. Binary sounds good, but what exactly? Oops. Base conversion to what? Sort by first letter. Okay, the lengthy description sounds good. You have to somehow store the length inside the encoding. All right, very good. So yes, I would say if you have to store a string and you don't know its length, the only thing you can really do is store the length first, followed by the string. There's many ways to do this. There's also a way, I think no one mentioned this. No one mentioned the other alternative, so maybe you're not C hackers. How would C represent a string? Well, it would write down the characters I don't know, C1, C2, C3, C4, and then it would stop with this special character null, which is not a 0, it's the character with ASCII code 0. So the null character means this is the end of string. That's something we've actually used before. That's our $. So you can cheat your way around this problem by adding another symbol to the alphabet. So by reserving a special character to mark the end of the string, you can get around this problem of not knowing the length. You don't even have to write it down. The other option, say Java arrays, do this. They would just start storing the length, and then followed by as many characters as you need. That's the two options that you have. Now for encoding, this is for encoding, we don't like this because it adds another symbol to our alphabet, and we have to encode this. We have to make this possible at any position. Now storing the length, there's still the question how to store the length, because we started with numbers in the first place. Sounds like both of these solutions don't immediately get us there. So let's think about this for a moment more. The solution will be called Elias codes by the person who invented them. And it's a prefix-free encoding, so that's important again. Prefix-free means that no code word is a prefix of any other code word. That means we always know when to stop reading. There's no position where you start reading some bits of your bit string in decoding and you don't know whether you should stop here and take it as one number or continue, because it might be another number. It will always be unique. All right, but it should be able to represent all integers. There's infinitely many of those, and we don't know any bound on how big they can be. Well, there's a very simple such encoding, and that's called the unary encoding. Forget about being fancy and forget about lengths. Let's just write the numbers as runs, right? That's what it is. 7 becomes a run of 7 zeros followed by a single 1. Okay, you could say this is actually the end of word character, but instead of adding a new character, I took a character from the alphabet away and encoded the words using the remainders. And because I started with a binary alphabet, there's only one character left, just the 0. So the only thing I can really do is repeat that 0 as many times as I need. That's great, problem solved, but oh, that's much too long. And also, we started with run length encoding. We wanted to get rid of those long runs. It's not much use to encode those long runs, the length of the long runs, by new runs. So that's clearly not what we want to do. The refinement that Elias came up with, and specifically the Elias gamma code is what we'll use. The refinement is, let's keep binary numbers and represent them with binary digits as usual. But before you write down the binary digits, you write down the length of the binary representation. And for that you use the unary code. But that's fine because the length of the binary representation is only logarithmic in the value of the number. All right. So let's see some examples for that. And well, Elias found that we can squeeze a few bits if you look at this closely. First of all, we always need, if we store numbers starting at 1, 2, and so, we always need at least 1 bit to represent the number. So we might as well store L-1. And the binary representation of any positive integer starts with a 1. So there's no real need to store this terminating 1 that we used for the unary code. So we can store L-1 by exactly L-1 zeros, and we don't need the extra terminating 1. That one will automatically come from the binary digits. So one example. The number 1 is just represented by 1. That's a short way of writing no zeros. So L would be 1 because we had 0 zeros. And then the binary representation of 1 is just 1. For 3, we see a single 0. So there's 2 digits to follow, 1, 1, and that represents the number 3. And so on and so forth. That's Elias gamma code. And that's able to represent any number as big as you like by just using enough zeros. But if you compare the lengths of those two representations for the same number, you see that this is linear in the value of the number, whereas this is 2 times the logarithm. So that scales much better to larger numbers. Because it was so nice to see you guys working, let's see how you can decode this. So I'll start the question and then show this explanation again. I think 2 minutes should be enough for this. So the point is, this is the beginning of a bit string, and I don't tell you where the first number stops. You should decode from this the first number in Elias gamma code that you find, and then just stop. So I want to hear a single decimal number from you. And again, well, maybe we can squeeze both of this here. So here you also have the rules for how to do it. Okay, I'll give you some more time to concentrate and work this out, because I think an example helps to understand this. All right, let's see how this went. I hope, despite the fact that you had to concentrate and calculate, etc., you can also appreciate the elegance of this code. Okay, a few of you were actually decoding all of it. That was more work than I intended you to do. 13 is the right answer. I can show you in a sec why. And of course, it's easy to go wrong by just making a slight mistake, and then all the rest won't work. Okay, so if you've only had 1 minute, it might be a little tough. But it's easy to come up with more examples for this. So why is it 13? The way to decode Elias gamma code is you start reading zeros. There's 3 zeros. That means the length of the binary representation is 4, 3 plus 1. That means what I have to read next is 4 bits. And that's a binary number. So 1101 base 2 happens to be a plus 4 plus 1, so that's 13. All right? That's how you would do it. And that also tells you that this is the end of the first number. And then you would continue with the next one. There you would see 0 zeros, so you read a single 1 digit, so that would be the number 1. And so on. Well, you can work out the rest if you like as an exercise. Run length encoding now uses Elias gamma code to store the length of the runs. So let's see that in an example too. Remember, we start, so this is encoding, we start with this bit string, and we start by writing down the first bit that we see. Then we store the length of the first run, which is 7 ones. So we encode 7 in Elias gamma code, and that happens to be this. Then there's 2 zeros, that's a 2, so we encode the 2. Then there's a single 1, which is encoded as a 1. Then there's a 20, a long run, that happens to be encoded to this. And finally, a run of ones, 11 ones, is encoded to this. And one more time, an example for the decoding as well. Well, you can work out the compression ratio by just taking the length of those two bit strings. Obviously, this became much shorter because it contained long runs. So we compressed it to 63%. That's not too bad. Now, decoding does the opposite. First, we find the first bit is a 0. So we start with runs of zeros. Then we decode, after the 0, we decode the number of zeros is 3 plus 1 means we have to read 4 bits. Oh, that's the 13 again. We know that already. So the output starts with 13 copies of 0. After that comes ones, and how many is given by the next Elias gamma coded integer. So 2 ones says we have to read the next 3 bits as a binary number. That works out to be 4. So here's the 4 ones. The next one, no zeros, so we read just a 1, and that means the number is 1, so there's a single 0. Then the next run again will be ones. There's 1 0, that means we have to read 2 bits. That's those 2, that work out to 2, so that's the 2. All right, I hope with this example, in case you didn't get it, you can go through it again in slow-mo. It should be clear how this run length encoding works and how you can encode and decode. How well does this compress text? First of all, it is used in some image compression formats, especially those that were targeted at black-white scanned images where you have lots of those runs. You can extend the whole idea to larger alphabets. In that case, it's not enough to say the length of the run is that and that. You also have to tell what the next character is, because it's not only a single choice. Other than that, that's a trivial extension. The whole compression scheme, run length encoding, is simple. That also makes it fast to apply. And we can compress some extreme forms of repetitive texts very, very much. If we have n bits that are all the same, we can compress this to essentially 2 log n bits. That's way, way less. So this is much more effective in extreme cases than any Huffman scheme would have been. As long as you encode things with individual character codes, you essentially hardly get below the linear amount of space. You still need at least 1 bit for each character, and that bounds how well you can compress, but not so for run length encoding. The downside is, for most types of data, you don't expect to see these repetitions. If you think about natural language text, English prose, you don't have so many words with 20 A's repeated. If you work out the details, count bits, you will see that the runs have to be longer than 6 bits, so that the scheme as I presented it actually achieves any compression. And for run lengths 2 or 6, there's these 2 isolated values, then the run length encoded version is actually longer than the original bit string. Remember, this kind of expansion is inevitable for a compression scheme. We've had this no free lunch statement at the beginning of this unit, and you will prove something about this in the tutorials. So it's not surprising, but 2 and 6, that's still fairly common run lengths in many types of data. So we need a more powerful compression method for the typical data types that we want to compress.